Dijkstra's algorithm is an algorithm used not for finding the minimum spanning tree, but instead for finding the shortest distance between two nodes. It can be any two nodes, or you can even find the shortest distance from one node to every other node in the network. Okay. Dijkstra's algorithm itself has quadratic complexity. However, if you want to find the shortest distance from every node to every other node using Dijkstra's, you would need to perform Dijkstra's algorithm n-1 times, where n is the number of nodes, making it a cubic complexity problem. Okay. Just to remind you, prims and crosscalls both have cubic complexity. Okay. You need to know those three. Prims and crosscalls have cubic, Dijkstra's has quadratic. Throughout the use of the algorithm, we use a box that looks like this. And one of those boxes goes next to every node in the network. Each section has its own title, or own bit that goes in there. So this one is referred to as the order. This one is referred to as the P label, which is the permanent label. And this bigger box at the bottom is referred to as the T label, which is the temporary label. The order, that's just going to be the order in which you select the nodes. So the first node you select is going to have a 1 in there. The fifth node you select is going to have a 5 in there. There's nothing too exhaustive. The P label is the permanent label. The number that goes in there is the shortest distance from that node to the node where you started. And in the T label box, there'll be some workings. So there'll be some other numbers in there. Some of them may be crossed out, okay, as we work through the algorithm. It's very important you don't get the P label and the order mixed up, because if you get those the wrong way around, you will lose marks. Okay, so you must make sure that the order is on the left and the permanent label is on the right. So let's apply this to a network. So here we have a network. I want to find the shortest distance and route from node A, which is here, to node G, which is over here. So what I'm going to do is put one of these double boxes next to every node, like so. And the good thing is, in the exam, these boxes will be drawn next to the nodes for you. Okay, the exam don't expect you to waste time drawing these boxes, because there are more important things for the exam to assess you on. Okay, so the network and the boxes will already be drawn like that. Okay. So we want to find the shortest distance from A to G. So I'm going to start at A, which means that A is the first box I've labelled, so it gets a 1 in the order. And the P label, well, that's the shortest distance from A to A. And that's, of course, always going to be 0 wherever you start. Okay, so the starting node will always have a 1 and a 0, and the temporary label box will be empty, because there's no workings needed. Now, once we've labelled a box with a permanent label, we update all the adjacent nodes. So the adjacent nodes to A are B and C, the two nodes that connect directly to it. And we take the permanent label of A and we add the distance to get to our adjacent nodes. So in this case it's a 6 to get to B, or it's a 3 to get to C. Now that we've updated the adjacent nodes, we zoom out, we look at the whole network, and we choose the smallest temporary label that doesn't have a permanent label. Okay, I'll repeat that one more time. We zoom out, we look at the whole network, and we choose the smallest temporary label that doesn't have a permanent label. So in this case, that is C. Okay, there are two nodes that have temporary labels that don't have permanents, B and C, and this is the smallest. So this is the second node I've chosen, so I get a 2 in there, and the total distance is the 3 that I've just written in the temporary label. Now that I've made that one permanent, I update the adjacent nodes. And I keep repeating that process until I get to G. Update the adjacent nodes. 3 plus 12 is 15. So 15 gets put in that temporary label. A 3 plus 5 is 8. So an 8 gets put in that temporary label. Now that I've updated the adjacent nodes, I zoom out. I look at the whole network and I choose the node that has the smallest temporary label that doesn't have a permanent label. And I say zoom out with emphasis because it's very easy to jump to E because that's the smallest one you've just updated. However, looking at the whole network, it's B we need to choose next. There are 3 nodes that have temporary labels and no permanents. We choose the smallest of those 3, which is B. So it's the third node I've labelled, and it's a total distance of 6 from A. That's the shortest distance from A to B is 6. And now I update the adjacents. Adjacent to B is D. I don't need to update A because that's been and gone. D, 6 plus 8 is 14. 14 is smaller than 15. And if you get to a point where you've got a number which is smaller than, then you can replace it. So we'll put a 14 next to it and I'll put a line through my 15. That tells us that actually the 15 that came from A to C to D is actually a shorter route. And the shorter route would be from A to B to D. Okay. Now that we've updated the adjacent nodes, we zoom out, we look at the whole network, and we choose the smallest temporary label that doesn't have a permanent label. And that would be E. Okay, so E is the 4th node I'm choosing, with a permanent distance of 8. Permanent label of 8. Update the adjacents. So 8 plus 20 is 28. That goes in that temporary there. 8 plus 3 is 11. And that's going to replace the 14. Oops, my box is a little bit small, so it's gone out. Okay, there's no other adjacents because C has been and gone. We can ignore that. And now we zoom out, we look at the whole network, and we choose the smallest temporary label that doesn't have a permanent label. In this case, that's D. So we get a 5 in there because it's the 5th node I've permanently labelled, and it gets a distance of 11. Update the adjacents. 11 plus 9 is 20. That's going to replace the 28. 11 plus 5 is 16. And now zoom out, look at the whole network, choose the smallest temporary label, doesn't have a permanent, and that is G. So 6 goes in there, and 16. And now that I have reached my destination node, I can stop. That's the algorithm complete. All I need to do now is perhaps underneath the network, state the resulting distance, and maybe find the route. Okay, depending on what the question is asking you to do. So in this case, the shortest distance is equal to 16, because that is the permanent label of G. That is a permanent label of G. The route, you could trial and error it, but the mathematical way to do it would be to take the permanent label, subtract an arc length, and if it equals the permanent label of that node, then you're on the right route. So 16 minus 2, well, that doesn't have a permanent label, so it's not that way. 16 minus 5 is 11, so the route goes this way. And you work from the end back to the start to get the route. 11 minus 8 is not 6, so it's not that way. 11 minus 12 is not 3, so it's not that way. 11 minus 3 is 8, so we head this way. 8 minus 5 is 3, so we go that way. And then 3 minus 3 is 0. And there we can see our route. That is the shortest route from A to G. And we can label that as A, C, E, D, G. And that's the answer.